Regular octagon A1, A2, A3, A4, A5, A6, A7, A8 is inscribed in a circle of area 1. Point P lies inside the circle so that the region bounded by PA1, PA2, and the minor arc A1, A2 of the circle has area 1/7, while the region bounded by PA3, PA4, and the minor arc A3, A4 has area 1/9. There's a positive integer n such that the area of the region bounded by PA6, PA7, and the minor arc A6, A7 is equal to 1/8 minus root 2 over n. Find n. So we have our regular octagon inscribed in a circle of area 1, and point P lies inside the circle so that the region bounded by PA1, PA2, and the minor arc A1, A2 has area 1/7. PA3, PA4, and the minor arc A3, A4 form a region of area 1/9, and we need to find the area of the region bounded by PA6, PA7, and the minor arc A6, A7. It's equal to 1/8 minus root 2 over n, and we need to find n. So clearly, this problem has more to do with finding the displacement of P from the center of the octagon and the circle instead of finding the actual distances from P to the sides. We know that if P were located right in the dead center of the octagon here, call that point O, then everything would have area 1/8. The area of the region bounded by OA1, OA2, and the minor arc A1, A2 is a 1/8 sector of the entire circle of area 1. So it's going to have area 1/8. But that's not the case for P. The area of the region bounded by PA1, PA2, and the minor arc A1, A2 is actually 1/7, which is a little higher than 1/8. So we need to find the displacement from O to P in the vertical direction, perpendicular to A1, A2. We know that point P satisfies the area of PA1, A2 minus the area of OA1, A2 is equal to 1/7 minus 1/8. Now the area of the region bounded by PA1, PA2, and the minor arc A1, A2 is the same thing as triangle PA1, A2 plus the region between A1, A2 and the circle. Same thing for the region bounded by OA1, OA2, and the minor arc A1, A2. That's just triangle OA1, A2 plus the region I've just shaded. Both areas are just the area of a triangle plus the area of the shaded region. We can subtract the shaded region from both of them, and it's just the area of each triangle would result in the same difference. 1/7 minus 1/8. That's equal to 1/56. So PA1, A2 minus OA1, A2, the difference in areas is 1/56. And the difference in their areas is a function that is dependent on the length of their common base. Let's call that D. More importantly, it's also dependent on the distances from P and O to A1, A2. So we can see that P is further away from A1, A2 than O because 1/7 is larger than 1/8. So if we draw this height in, let's call it HO. And then HP is the height from P to A1, A2. Let's place P, I don't know, somewhere here. Point P. To A1, A2 has distance HP. And now we can form an equation in terms of HO, HP, and D. We have that the area of triangle PA1, A2 is equal to 1/2 D times HP. And the area of OA1, A2 is 1/2 D times HO. That's equal to 1/56. So 1/2 D times HP minus HO is equal to 1/56. If we multiply by 2, D times HP minus HO is equal to 1/28. And then dividing by D gives HP minus HO is 1/28D. So the distance from P to A1, A2 is 1/28D greater than the distance from O to A1, A2. And now let's do a similar thing with PA3, A4 and OA3, A4. We know that the difference in their areas is equal to OA3, A4 minus PA3, A4 is equal to 1/8 minus 1/9. Because if you add the shaded region to both of them, you're going to get 1/8 and 1/9. So without the shaded region on each of those areas, the difference is still the same thing. So OA3A4 minus PA3A4 is equal to 1/8 minus 1/9. That's equal to 1/72. Let's use a different variable to represent the heights from O and P onto A3, A4. I'm just going to call them NP and NO this time. And A3, A4, of course, is also equal to D, because it's a regular octagon and all sides have the same length. And now let's write another equation. The area of OA3, A4 is equal to 1/2 D times NO. And the area of PA3, A4 is 1/2 D times NP. This difference is equal to 1/72. So if you multiply by 2, you're going to get the D times NO minus NP equals 1/36. So you get the difference in heights between O and P to A3, A4 is 1/36D. So now it makes sense to coordinatize the whole thing. We can let O be the origin at 0, 0, and then point P, well, its x-coordinate is the horizontal distance between O and P. That's just NO minus NP, which is 1/36D. And its vertical coordinate is the negative of the difference between HP and HO. P is located below O vertically. So it's going to have a negative y coordinate, and that's equal to negative 1/28D. So now that we've found the coordinates of O and P, it's a little easier to find the area of the region bounded by PA6, PA7, and the minor arc A6, A7 in terms of 1/8 minus √2/n. Let's just delete everything we found earlier. We no longer need that anymore. We're only going to focus on A6, A7 now. Well, we know that OA6, A7, the region bounded by OA6, OA7, and the minor arc A6, A7 is equal to 1/8. Because O is the center of the entire figure. We know this region has area 1/8. Now, what would happen if we moved O over to P? Well, then the distance from P to A6, A7 would be a little less, resulting in a lower area at 1/8 minus √2/n. But exactly how much less is the question? Well, that depends on the difference of the distances from O and P to A6, A7. Just to verify that P is closer to A6, A7 than O, it makes sense because the parallel line to A6, A7 that passes through O, if it passes above P, then P would be closer. And yes, because the x-coordinate of P is less than the negative of the y-coordinate of P. 1/36D is less than 1/28D. So if we were to draw this line that passes through O and is parallel to A6, A7, then P lies below that line. And in fact, this line is just the line y equals negative x. So the areas of the sectors OA6, A7, and the region bounded by PA6, PA7, the minor arc A6, A7, are 1/8 and 1/8 minus √2/n, respectively. So OA6, A7 minus PA6, A7, we can write that's equal to just 1/8 minus 1/8 minus root 2 over n, which is just root 2 over n. And what is this equal to? Well, that's just equal to, remember, the side length of the octagon is equal to d. The area of triangle OA6A7 is d over 2 times the distance from O to A6A7. And the area of PA6A7 is d over 2 times the distance from P to A6A7. And this we can say is equal to root 2 over n. So if we multiply by 2, then d times the difference of the distances from O and P to A6A7 is equal to 2 root 2 over n. But what is this? The difference of the distances from O and P to A6A7? Well, that's just the distance from P to the line y equals negative x. See? Because this distance, the distance between the two parallel lines, and the distance from P to A6, A7, if you could just move this here, there's only one thing that would remain, and that's this little thing over here, which can be represented as the distance from P to that line y equals negative x. The difference, as you can see, is just this little tiny thing right there. That's the distance from P to the line y equals negative x. D times the distance from P to the line y equals negative x can be represented as 2 root 2 over n. And we already know the coordinates of point P. So we can figure out its distance to the line y equals negative x, better represented as x plus y equals 0. The distance from point x1, y1 to the line x plus y equals 0. Well, that's just x1 plus y1 over the square root of 1 squared plus 1 squared, which is x1 plus y1 over root 2. This is the directed distance from point P to the line y equals negative x, or x plus y equals 0. But if you want the absolute distance between the point and the line, you have to take the modulus of x1 plus y1. And the coordinates of point P are 1 over 36d and negative 1 over 28d. So what would x1 plus y1 be equal to? Well, that's just 1 over 36d minus 1 over 28d divided by root 2. And in the end, we want this to be equal to 2 root 2 over n times d. I'll write that down here. The distance between P and the line y equals negative x is 2 root 2 over n times d. So 1 over 36d minus 1 over 28d divided by root 2. Well, if you take a least common multiple of 36 and 28, that's 252, 36 times 7 and 28 times 9. So 7 over 252 d minus 9 over 252d over root 2. So this is just 2 over 252d, all divided by root 2. And that's just root 2 over 252d. And putting it in the form we wanted, with 2 root 2 on the numerator, that's 2 root 2 over 504d. Therefore, we see that n is equal to 504. So going back up to the problem statement, 1/8 minus root 2 over n, the area of the region bounded by PA6, PA7, and the minor arc A6, A7 is equal to 1/8 minus root 2 over 504. Thank you for watching this YouTube video. The AIME 1 is in 5 days. So good luck on the AIME 1 if you're taking that. Or AIME 2. Please follow my channel if you would like to see more videos. I would like to reach 300 followers before the AIME 1 in 5 days.